Hello, welcome to the Lean and Six Sigma integration simulation. How many of these have you heard of? Zero inventory, management by objective, zero defects, total quality control, just in time, optimized production technology, synchronous manufacturing, continuous improvement, Kaizen. Let it be said that we've heard all these. We've lived through all these. They have come into vogue and they have gone away. We're talking about Lean and Six Sigma. These methodologies have been around for a long time and they will continue to be around. They will outlive all of these on this slide. The purpose of our simulation today is to experience the impact of certain strategies on customer satisfaction, continuous improvement, and the elimination of waste. These strategies are: how does overtime impact things? How does less variation in a process impact? We're going to look at these impacts. We will understand material flow in a linked process. What is a linked process? A process where you have to do operation A before B, B before C, C before D, etc. They are linked. They go in order. We're also going to learn about the impact of inventory on performance, high inventory versus low inventory. How does it impact the ability to react to change, meaning delivery time, quicker part process problem solving detection, quality? What does high inventory versus low inventory have to do with quality? We're going to look at that. We're also going to see how to improve manufacturing lead time. High inventory versus low inventory. How does this impact lead times? We will also see during this simulation the impact of varying process yields on the manufacturing team. This slide demonstrates that we have put a bottleneck in the middle of our process. We're going to see what happens. What do bottlenecks actually do to our throughput and our quality and our cost? So the simulation setup has already occurred. You'll see that on the Module 1 video. Each person has 4 chips in front of them. There's 1 die for each position. There's a placemat with shipping instructions and an operation number card. The supplier is the person immediately to the instructor's right, first operation within a process, and they have all the chips. That means they can fulfill anything coming into the process. This is our factory. The die represents the yield from the equipment. You can roll a 1, you can roll a 2, you can roll a 6, you can roll a 1. That variation simulates the machine operating on the factory floor. Machines vary in production due to downtime, operators, etc. We're going to represent that yield variation from the equipment with the die. The chips will be the number of parts produced per day. So if you roll a 4, you will have produced 4 parts. Nothing complicated, it works exactly like in real life. Our die has 6 sides with a different number of dots on each side. There's 21 dots total on a die. We're going to divide that by 6, gives us a 3.5 average. We will work 20 days a month. No Saturdays, no Sundays. That means we should be able to produce, on average, 3.5 times 20 days, or 70 units. This is 50% of our capability. What do you think is going to happen? 50% should be a breeze. Now, since we're running a factory, we need to have operating costs. We need to have a production cost breakdown. We need to be able to tell, are we making money or are we losing money? So in order to do that, we're going to use average operating cost overall to give us a production cost breakdown. In this slide, you can see the material represents roughly 50% of total operating cost. You have labor, inventory, which is work in process, and manufacturing overhead. Now, labor costs are the number of people times 20. You will see us figure out the number of people in the room, how many are working, and we're going to take that number and multiply it by 20. Overhead cost, that becomes our labor cost. Overhead cost is 1/3 of the labor cost that we just calculated. The inventory cost, or the WIP, is the amount of starting inventory less the supplier. His hasn't been put into the system yet. So everybody but the supplier will have 4 chips in front of them on each module. The material cost is what we pay for material to produce the product. Total cost is the labor plus the overhead plus the inventory plus material cost. It's all the costs combined. Unit cost is how much does it cost us to produce one part. That's the total cost divided by the throughput. So if our total cost comes out to be 500 and we produced 50 parts, our unit cost would be 10. Lead time is the number of days to go through the system. Now, when figuring lead time, you give 1 day for new chips to be added to the system. In our case, in each module, you'll see that we will use a new color of chips at the start so that we can track when the new color gets into the warehouse. We'll take that number of rolls minus 1 for the introduction, and that will be our lead time. Now, we have a factory. We're going to have standard work rules. We're going to run 1 shift per day will be worked. Each module represents 1 month. 1 month is 5 days per week times 4 weeks equals 1 month, or 20 days equals 1 month. The material must be processed before it can be passed on to the next operation. That means all you have is what's in front of you when you roll the die. If you have 3 parts in front of you and you roll a 4, you can process those 3 and those 3 only. You cannot add to make up the missing piece. Okay, so the material is moved at the end of the shift. This would represent, if we shift ended at 4 o'clock, we shipped at 3:59. So whatever is coming in is not available for that roll, but available for the next day, the next roll, not that roll. Material is moved at the end of the shift. You will see that on the module. Only move what is in front of you when the dice are rolled. All the stuff coming to you is for tomorrow's work, not today's. Parts that have been processed are to be shipped to the next operation. You will see this occur when I say ship. People will be shipping. They will be moving their product. Again, I can't stress this enough. Material movement is at the end of the ship. You can only process what is in front of you at the start of the shift or when you roll the die. All incoming material arrives at the end of the shift. So this is module 1. You will see this occur. What this does is teaches us what is happening in our work rules. So module 1, we're going to have an inventory of 4 units. Everybody has 4 chips in front of them. We're going to have a transfer batch size of 4 units. And we're going to have material movement at the end of the shift. And we're in a functional layout. So if you see as you look at the video of module 1, you will see people getting up and moving. Why are they getting up and moving? Because this is how we have laid it out. This is very similar to real life, where we lay out a factory or we lay out a plant. We put a new process coming in an empty space. Does it have anything to do with flow? No. So that's what's called a functional layout. Now the transfer batch size is how many parts can you move at the end of the shift when you move your parts. You can only transfer 4 parts at a time, not 5, not 3, not 2, not 7, only 4. You will have an opportunity to possibly transfer 4 units or 8 units. If you have that, please transfer 8. Watch what happens. Watch during the video, watch what we have done to our process. Okay, we can see at the end of our module, we can see lots of movement, lots of people running around and everything, but we did not make throughput. We only got 44 pieces instead of 70. Why? Why did we only get 44 pieces? Could it have something to do with our layout? Could it have something to do with restrictions? Our big problem was we didn't get 77 pieces. The reason we didn't make our production throughput of 70 pieces is there were shortages that we encountered during the month. Being short of parts when the machine could have processed them. Only had 3 parts, could have processed 6. What caused these shortages? The constrictions that I put on the system of shipping only 4 parts meant that this would happen. When I restricted the amount of parts we could ship from operation to operation and only put it at 4, it's like saying, here's your batch size. You will operate in batch sizes of 4. Now you understand why a lean Six Sigma guy is very against batch sizes. Are all batch sizes bad? No. If you can get away with smaller batch sizes, that's the way to go. But we created the shortages because we made our batch size 4 parts. So how do we overcome shortages? Typically, for in production, we put more production, more parts into the system. Is that the best solution? What about quality? High inventory creates quality nightmares. You have to move the material, it gets damaged in the movement. You have to keep track of it. You lose sight of some of it. There's changes that occur in the design. All have to be scrapped out if you have high inventory levels. So the quality is definitely suspect when we have higher inventory levels. What about the cost of the inventory? Storage space, material cost, processing cost, all for material that's sitting there, not going to be sold. That becomes a waste and non-value. Waste and non-value is anything the customer doesn't want to pay for. I don't want to pay for excess inventory. That's your issue. So, is excess inventory the best solution? No, it is not. For our purpose, for our simulation, how do we fix this? Well, it's simple. We take the restriction of 4 parts per transfer off. We say if you have 1 part, you can transfer it. This equates to eliminating batch or batch sizes. I am a big fan of one-piece flow and not worrying about batch sizes. Batch sizes slow production down. We want to eliminate batch sizes, or at the very best, we minimize them as much as possible. So there's 3 ways to lose a customer: cost, delivery, quality. Old thinking has a percentage of repairs built into the system, meaning if I produce 100 parts, 4 of them I'm going to have to repair. Well, that's too high a number. Six Sigma thinking is 4 defects per million parts, where the process is stable and consistent. We want to look at it to make sure that our costs are minimal, our delivery is on time, and our quality is as high as it can be with 4 defects per million parts. Now, we did not measure, in which really we're not going to measure, but I want to bring it to your attention. We had a functional layout where operation 10 fed operation 20. This is a linked process. Operation 10 fed operation 20, 20, 30, 30, 40. Lots of moving here. A lot of people getting up and moving around. Lots of chances for transportation failure. Lots of chances for inventory quality to go down. Lots of, just can't see the beginning and the end. This is a functional layout. What would make sense to improve this? Well, what if we took the functional layout and changed it? What if we changed it to a focused layout where we had the operations in order, creating flow through the entire system? Would that help us? Would that hinder us? This would be the way we want our plants to be laid out. Is your plant laid out in a functional layout or a focused layout?